Thanks to the organizing committee, to the scientific committee for the invitation. It is a great honor and great pleasure to give an opening lecture at the Latin American Congress. So it is really fascinating to watch how mathematics is flourishing in Latin America, and it is very interesting, of course, to visit Colombia for the first time. And also, I should confess that I have never dreamed that I would be an actor in Colosseum, so it sounds like, like a serious business, so a matter of life or death, so I will try to survive. Okay, so and with that, let me pass to the mathematics. So, well, now it should be rescaled. So oh, yeah, it's better. Okay, so as it was announced, I will be talking about renormalization and area of the Julia set. So this first slide may be most important. So just to give you a very general idea what renormalization is. So the notion, it was developed first in physics, in particle physics, in statistical mechanics, and actually before in quantum field theory. So the general idea was that our physical space looks differently in different scales. When we probe the space in different scales, that we should recalculate the physical parameters. And the renormalization gives us this procedure of recalculating the physical parameters. And first it emerged as just a technical tool to regularize certain integrals, and then it was realized that it is really fundamental physical notion. So it happened in physics in the 50s, 60s, 70s, and then in the mid-70s, this idea was brought to dynamics. So kind of the same kind of idea generally. So we have some phase space for our dynamical system. So here is a caricature for our phase space. So you can think, to start with, you can think from just an interval, just real line or complex plane, a simple phase space, and some simple class of maps F acting on this space. And we want to understand the iterates of this map. The dynamics is a qualitative understanding of iterates of this map. And so as in physics, we want to understand this somehow, these dynamical systems in all scales. The key is to have some uniform idea of how this dynamical system looks in different scales and how to recalculate, how it should be recalculated in various scales. So in dynamics, it actually assumes a very simple form. So take some little set in your phase space. So that is your scale in which you want to understand your dynamics, and just take a point and start to iterate this point. So it goes around, and at some time it can return back to this little part of this phase space. In this way, you define a return map. And this return map to this little piece of the phase space. And this return map can happen to look like the original system. So in other words, you may have some initial space of dynamical systems you're interested in. So, and when you consider this return map, all of a sudden you bring yourself back to this original space. Of course, it should be good luck. It is not just random choice. So you should be lucky enough to see such kind of situation. And then what you do, you take this little piece and you rescale it roughly to the original size and conjugate your initial map F to the new map. And this new map is called the renormalization of the original map. So in this way, if you are lucky, you obtain some renormalization transformation which associate you to some class of maps F, their renormalizations, and renormalization is just the same dynamical systems in small scale. And then maybe you're again lucky, you select your favorite scale here, consider the return map, and maybe you again bring yourself back to the original class of maps, you rescale it, and you obtain the second renormalization, etc., etc. So of course you could be unlucky, it could be repeated several times and then you cannot do anything, or you could be lucky so that it will continue forever and then your map is infinitely normalizable in the sense of this renormalization operator. Okay, so you have some sequence of dynamical systems responsible for the dynamics in various scales. Well, but it's not enough. Your space of maps could be very big space, and so this does not give you real control in small scales. What you really want is that in all scales, your dynamical system looks roughly the same. So, and the property which is responsible for that is called a priori bounds, and it says that all these renormalizations form a precompact family. There is much smaller subspace, compact subspace of maps, so that eventually renormalizations are brought to this precompact family of maps. And if you have a priori bounds, and of course it should be a big luck, and it is usually very difficult to establish this kind of property, but if you're lucky and you manage to establish such kind of a priori bounds for your dynamical systems, what it means? It means that you can control your dynamical systems roughly uniformly in all scales. And it is certainly a big deal. But then you go even wilder. So you don't stop here. You want better than that. You now guess that there could be just some dynamical system in your space, some map F star, which does not change at all in all scales. So it is just invariant with respect to your normalization operator. So this first return map rescaled, and it is highly nonlinear operation. All of a sudden, you want the new map RF to be equal to the original map F. Of course, there is no a priori reasons to assume that it could be the case, but we are an optimists, and so we guess that there could be such a very special map F star which looks exactly the same in all scales. In other words, it is the renormalization fixed point. And moreover, you just want this renormalization fixed point to be very special, so with respect to this renormalization transformation. Remember, renormalization transformation is now a new dynamical system acting in the infinitely dimensional space of maps. So here is a caricature of our infinitely dimensional space of maps, and there is a fixed point there, and you want this fixed point to be hyperbolic with respect to the renormalization transformation. What does it mean to be hyperbolic? It means that there is a stable manifold, and you want the stable manifold to be finite codimension, such that it consists of all maps which are infinitely normalizable in this sense. And if you take this infinitely normalizable map and start to iterate it, so then you will converge exponentially fast to the renormalization fixed point. So the space of infinitely normalizable maps is finite codimension submanifold, where the iterates of renormalization converge exponentially fast to F star, which means that if you take infinitely normalizable map, that not only in all scales they look roughly the same, but actually in deep scales they look exactly like the fixed point F star, up to exponentially small error. So it's a lot to ask, and this property is referred usually as dynamical rigidity or dynamical universality. So all infinitely normalizable maps look the same, geometrically the same, not just qualitatively, geometrically the same in small scales. And how they look is controlled by this renormalization fixed point F star. And you want also to have a transverse submanifold, finite dimension submanifold W, which is called unstable submanifold, which is partially invariant with, which is mapped to something bigger under renormalization, and the orbits under the normalization transformation, if you take a point close to the fixed point, then under normalization, it will exponentially fast escape through this unstable manifold. And so this unstable manifold corresponds to changing of the essential parameters of the dynamical system. So you change combinatorics of the maps. Your maps are not infinitely normalizable anymore. They can be only finitely many times normalized. But in this unstable manifold, you have some picture of bifurcations. How bifurcations look like in the direction transverse to your combinatorial class of infinitely normalizable maps. And if you have such a normalization picture, then the conclusion would be then bifurcation loci look self-similar near this fixed point, and moreover, they look the same in different finite parameter families. In this unstable manifold or in any other finite parameter family transversed to the stable manifold, the bifurcation loci will look geometrically asymptotically the same near the corresponding point, infinity normalizable point. And this property is called parameter universality. So that is somehow two very deep properties which are encoded by this renormalization picture if you are able to establish it. And of course the question, so why should we hope to have such a beautiful picture with such so great consequences? And it turns out that actually there are quite a few situations where this picture actually realized, and I will just illustrate you with several situations like that in low dimensions, in dimension 1, real and complex. So, and we'll give you some applications of this phenomenon. All right, so let us go to illustration. So the first example is very simple example. So now our phase space is really an interval, and you take some unimodal map on this interval. Unimodal means that there is one critical point here, just extremum of quadratic type, non-degenerate. The map you think is real analytic map, for instance, a real quadratic polynomial. And normalization would be the following procedure. So if you're lucky, you may have an interval here which is under dynamics, under some iterate comes back. So this periodic interval. So, and if it is so, you select this interval around the critical point. So for instance, under the third iterate, it comes back. You can rescale this interval to the original size, and this would be your renormalization. You see that this renormalization operator comes together with combinatorics, some combinatorial data. There are plenty of renormalization operators. I depicted here tripling renormalization operator, but there is a doubling renormalization operator with two intervals interchanged. Or for any period, actually, there is some renormalization operator, and there are actually several renormalization operators to higher periods, because there are several, these periodic intervals can be ordered in different ways on the real line, which determines combinatorics of renormalization operator. Combinatorics of this unimodal renormalization operator is a period together with the ordering of these intervals on the real line. And so fix your favorite combinatorics. For instance, I fixed here period tripling. And in the mid-70s, Feigenbaum and Collier-Tresser put forward a conjecture that actually exactly such a renormalization picture holds for each of these renormalization operators. And moreover, the unstable manifold is one-dimensional, unstable, has dimension 1 in this situation. So it was conjectured, it was motivated by physics, so I think that mathematicians would not come up with such a conjecture coming from nowhere. So, and it took about 20 years until mid-90s when this conjecture was actually confirmed. So there had been a deep development before, but so it was completed in the work of Dennis Sullivan, Kurt McMullen, and myself. It is a sequence of works, not a joint work. So where this conjecture was established for so-called quadratic-like maps. And I will tell you a little bit later, so what are these quadratic-like maps? So quadratic-like unimodal maps. So it is unimodal maps which admit certain kind of analytic extension with certain nice properties. So what are the consequences of such kind of theorem? Now in the mid-90s it became a theorem. Consequences is, as I mentioned, is dynamical universality and parameter universality. And so in this context, dynamical universality would mean that our map, so if you take your favorite combinatorics, say tripling, and you consider the map which is infinitely normalizable with respect to tripling, all such maps, then each of them has a Cantor attractor. There is a Cantor set which attracts almost all orbits on the interval. And the dynamics on these counter sets are topologically the same for all the maps. So if you take a map F, so restricted to this counter set, and the map G, another map G, infinitely normalizable in this sense, restricted to its counter set, then the dynamics will be conjugate. And moreover, this conjugacy will not be only topological conjugacy, but it will be a smooth conjugacy, C1 plus alpha smooth, which means that our counter sets have the universal geometry in all scales. That is manifestation of rigidity, of dynamical rigidity in this particular case, a consequence of the previous normalization picture. How about parameter rigidity? So here is an iconic picture in one-dimensional dynamics. So it is a picture of a quadratic, real quadratic family. That is a parameter line C, and it is a dynamical axis X. And what is depicted here for each parameter C, what is depicted is a limit set for almost all orbits of your dynamical system. For instance, in the beginning, here we have just a fixed point, attracting fixed point, which attracts almost everything. Then this fixed point bifurcates to attracting cycle of period 2, which attracts almost everything. Then it bifurcates to attracting cycle of period 4, which attracts almost everything, etc., etc. You have this cascade of doubling bifurcations. And what was observed by the Feigenbaum in 70s is that this sequence of doubling bifurcations converges to the limit point exponentially fast, and moreover, this rate is universal. So if you replace the quadratic family with some other family of the same qualitative type, then you will observe the same qualitative picture, and you observe this sequence of doubling bifurcations, and the rate will be universal. The rate will not depend on the family in question. This striking discovery actually prompted Feigenbaum to put forward this universality conjecture. And so now it is a theorem, and not only for doubling bifurcations, but for tripling and for any kind of bifurcations. And actually, if you refine, if there is a way to put all these renormalizations corresponding to doubling, tripling, etc., in one picture, to have a global renormalization operator, and it leads to essentially complete understanding of the real quadratic family from the probabilistic point of view. But I will not go in this direction, but rather will move forward to some other related types of renormalizations. So, so what is very fascinating about that development is that though it can be formulated in completely real terms, actually the proofs, at least in that work of Sullivan, McMullen, and myself, the proofs are going through the complex domain. So according to the famous principle by Penlever and Adamar, often a shortest path between two real points goes through the complex domain. So it's exactly what happened here. So in order to do that, we need to have some nice analytic extension of unimodal maps, and such an analytic extension is called a quadratic-like map. So quadratic-like map is now some disk in the complex plane, which is mapped by map F to a bigger disk holomorphically as a double branch covering. So there is one critical point here, but otherwise it is just a covering map of degree 2. Such maps called quadratic-like. So, and they could be viewed as dynamical objects. Though the phase space is not exactly invariant, it is mapped onto a bigger space. Still, we can take a point, we can start to iterate it, and see whether it stays forever in the domain of our map. Then we say that our point belongs to the field Julia set. So field Julia set is a set of points which never escape these smaller disks. So, so here, outside of the field Julia sets, the points escaped through this fundamental annulus. You cannot iterate anymore, so you stop. And by the way, the Julia set is a boundary of the field Julia set officially. So the Julia set is no variance. On my picture, somehow the field Julia set is equal to the Julia set, but it can happen that the field Julia set has no empty interior. And then its boundary, the boundary of this set is called the Julia set. So the quadratic, the simplest example is just to take a quadratic polynomial and restrict it to some big disk. And then you will obtain a quadratic-like map, and the Julia set of quadratic polynomial can be defined in this way. So here is, so here is some typical example of a Julia set for the quadratic polynomial. So here's this blue region and where the orbits escape to infinity. You can see that there is a big disk here and they escape from this big disk. This dragon is a field Julia set. The skin of the dragon is a Julia set. And there is a basic dichotomy which says that the field Julia set and the Julia set are either connected or countersets. And so if we take a quadratic family, z squared plus c, we can now look at some parameter c and ask ourselves whether the Julia set for the corresponding parameter is connected or it is a counterset. And this leads us to the famous picture of the Mandelbrot set. That is the bifurcation diagram for the quadratic family. So this blue region is counterset locus. So for these parameters in the blue region, the Julia set is totally disconnected. So it's a counterset. And if this red set is called the Mandelbrot set, it is exactly those parameters for which the Julia set of the quadratic polynomial is connected. And it is extremely rich set. Somehow you can wander around, blow up in different places, and you see fascinating pictures that could look somewhat differently, or sometimes there is some similarity, and people can just spend their life just wandering around this main cardioid of the Mandelbrot set, or studying what happens here near the cusp, or going further into the limbs of the Mandelbrot set. It is really fascinating and extremely rich set whose structure is conjecturally very well understood, but mathematically is not completed yet. So yeah, the study of the structure of this set. And so, as I mentioned, there are some self-similarity inside of this set. There are some little copies of the Mandelbrot set that you can find inside. So for instance, it is just blow up of the Mandelbrot set in some place, and you see some little copy which looks exactly like the whole Mandelbrot set. So why does it look like that? Not only topologically, you see that geometrically it is basically undistinguishable. There are some other copies, much bigger. You don't need to blow up. For instance, here, attached to this bifurcation point, there is some copy of the Mandelbrot set, so which is called the Dublin copy of the Mandelbrot set. And here there is another copy, which is called the Triplin copy of the Mandelbrot set. They look a little bit different. They don't have the cusp. Otherwise, they look pretty much the same as the big Mandelbrot set, but without cusp. This cusp is replaced with some bifurcation point where this copy is actually smooth. Okay, well, so how to explain presence of these copies in the Mandelbrot set, which looks exactly like the whole Mandelbrot set? And so the answer is given by the quadratic-like renormalization theory. The quadratic-like renormalization theory is like for unimodal, like renormalization theory for unimodal maps, but now you have a disk around the critical point. You iterate it, so you iterate this disk, and it can happen that it comes back under certain iterate as a quadratic-like map. And if this quadratic-like map, so for instance, in my picture, there is a fourth iterate of the original map, which returns back as quadratic-like map. And if the Julia set of this quadratic-like map, this red guy, is connected, then you say that the map is renormalizable. Actually, there is one extra technical assumption, namely, so you want these domains that you iterate to be almost disjoint. On my picture, they are disjoint, and if you can select the domains to be completely disjoint, then it is called primitive renormalization. If you cannot select them to be completely disjoint, it is called satellite renormalization. And this little technical difference is actually very deep, and lead to very deep differences in the types of these renormalizations. Okay, so and again, as in the unimodal case, the normalization comes together with its combinatorics. It is a period, and also it is the combinatorics how these little Julia sets sit inside of the big Julia set. You have the big Julia set of the original map, and you have these little Julia sets, and there is certain relative positions of these little Julia sets in the big. It's combinatorics of our normalization. You fix your favorite combinatorics, and you ask yourself a question. What are quadratic polynomials which are renormalizable with these combinatorics? For instance, with period 4, as depicted on this picture. And the beautiful answer was given in the 80s by Doherty and Hubbard. the answer is that it is exactly little copies of the Mandelbrot set which consist of parameters which are normalizable with certain combinatorics. You select your favorite combinatorics, like this one, period 4, with this placement of Julia sets, and then you can find some little copy of the Mandelbrot set inside of the Mandelbrot set, and all parameters inside of this little copy are normalizable with Z combinatorics, and only these parameters. Okay, so we now understand that as long as there is this kind of universality, we observe this, clearly observe this universality in the parameter domain, these little copies look exactly like the big Mandelbrot set. There should be some normalization theory that is responsible for this phenomenon. And so you guess that for this quadratic-like renormalization with a given combinatorics, there should be the same renormalization picture. The normalization operator in the space of quadratic-like maps should have a fixed point, some quadratic-like maps which looks exactly the same in all scales, and this fixed point should be hyperbolic. There should be stable manifold of codimension 1, unstable manifold, and this unstable manifold is responsible for this geometry. And actually, this could be justified. And this was what was done in the case of real symmetric quadratic-like maps in the work of Sullivan, Macmillan, and myself in the 90s. And actually, it was that theory applies to more general complex combinatorics, except that one needs a priori bounds. So if we have some nice a priori bounds, then one can justify this theory in the space of quadratic-like maps. And what is beautiful about this complexification is that these geometric properties that we are interested in, hyperbolicity, what hyperbolicity means? It means that some map is contracting in certain submanifold and some map is expanding in a certain submanifold. This geometric property in the complex world can be detected for purely topological reasons. So if your, say, combinatorial class can be endowed with certain complex structure, and there is some natural metric in this complex manifold or complex variety, for instance, some analog of classical Carathéa-Dore metric, which is contracted by all holomorphic maps, then you have a good chance that your renormalization so will be strongly contracted with this with respect to this Carathéa-Dore matrix. And that's exactly what happens in this situation. So the arguments from the 90s were a little bit different. So the idea, Sullivan exactly had this kind of idea of applying the Schwarz lemma to the renormalization transformation in the combinatorial class, but in most clean way, it was realized in more recent work by Artur Avila and myself, where this combinatorial class was endowed with Carathéa-Dore metric, and it was shown that a priori bounds, nice a priori bounds, allow to apply the Schwarz lemma and to see contraction in this combinatorial class. And similarly, there are some topological properties which allow to detect expansion. So we need this combinatorial class, which is codimension 1 submanifold. We have only one direction which is problematic. We want this direction to be expanding. And it turns out that if this direction is not expanding, if it is a neutral or attracting direction, then there is a small orbit. There is some map nearby here, some quadratic-like map nearby, which under renormalizations stay very close to the fixed point. And this could be ruled out by some rigidity theorem. So that is why complex world is so much more powerful than the real world. Well, in this occasion, just there are these wonderful tools like Schwarz lemma, ideas of hyperbolicity, etc., rigidity, which allow to derive geometric consequences for topological reasons. Okay. So, and this leads us to the dynamical and parameter universalities as in the general context. So now if we have infinity normalizable quadratic-like map, then all these infinity normalizable quadratic-like maps, they look the same in deep scales, and it's controlled by the renormalization fixed point. And it also explained why the Mandelbrot copies are so similar to the big Mandelbrot set, because there is this parameter universality which controls the shape of the Mandelbrot copies. But this, I mentioned that this depends on some kind of a priori bounds. These a priori bounds were, such a priori bounds were established in the real case in the 90s, but in the complex case, they were established more recently, about 10, 15 years ago, by Jeremy Kahn, who proved a priori bounds for normalizations with primitive combinatorics. Remember that we had this this difference between primitive combinatorics and satellite combinatorics, and primitive means that certain domains can be selected to be disjoint. And actually, it is reflected in the corresponding copies of the Mandelbrot set. So this copy of the Mandelbrot set, it is a primitive copy. You have a cusp here, it corresponds to a primitive renormalization. Here, Kahn's a priori bounds apply. And this copy, which corresponds to Dublin, is a satellite copy, or this copy corresponds to triplet. It is satellite copy. These copies don't have a cusp, and they are attached to the main cardioid, and a priori bounds don't apply. Kahn's a priori bounds cannot be applied in this situation, so this case is still open with respect to, so the normalization theory still stands open for these satellite copies of the Mandelbrot set. Okay, so let us now proceed further. So to different types of normalizations. So far we discussed normalizations for unimodal maps and for their complexifications, and more generally for quadratic-like maps. And now, so another class of maps are critical circle maps. So it is the maps of the circle. So it is analytic homeomorphisms of the circle, so which have one critical point of cubic type. And if you cut your circle into, at one point you obtain an interval, and this map would look like that. So just interval exchange map, nonlinear interval exchange map with two branches like that, and one critical point. I put the critical point of cubic type here. And there is a way naturally to define the renormalization of these maps, and combinatorics of this renormalization is exactly controlled by the rotation number of the map. So there is a very nice connection between number theory and dynamical systems here, and you can complexify, like in the unimodal case, you can complexify situations, so these circle maps will be, these circle maps can be complexified to butterfly maps. So you have two disks which are mapped to bigger disk with some appropriate slits. You should be careful here. It is, every time it is non-trivial to set up the corresponding normalization theory, but one can do appropriate setup of the normalization theory in this setting, and to carry the whole theory through, roughly speaking, following the lines of the unimodal and quadratic-like story. And this was done also in the 90s by Edson de Faria, Bennington de Mello, so from Rio, and Mikhail Polsky. So this normalization theory for critical circle maps. But now, so let us make one step further, and let us consider so-called Siegel maps. So what is a Siegel map? So it is, so it assumes that we have some analytic map, some holomorphic map in some domain, and it has a fixed point, and this fixed point is of neutral type. So the differential at this fixed point is just rotation by some angle theta. And moreover, not only the differential is rotation, but actually the map can be, assumes that the map can be actually linearized conformally near this fixed point. So there is a conformal conjugacy that brings our map to rigid rotation by angle theta. So this kind of situation is called Siegel situation. Siegel was the first to show in 40s that this kind of maps do exist. And the Siegel disk is the domain, the maximal domain on which our map can be linearized, on which our map looks like rotation. So here it is, this disk is called the Siegel disk. And so, and for Siegel maps, also physicists observed some self-similarity properties. For instance, here is the picture of a Siegel quadratic polynomial. there is a Ziegel quadratic polynomial. For instance, this one corresponds to the rotation number, which is the golden mean. Yes, so if you don't know what is the golden mean, please go to the logo of this Congress. So it is depicted there. So here is our Ziegel map. So this is the main Ziegel disk. So here is the fixed point sitting somewhere here, and the map is rotation here on the whole this domain. The map can be reduced to rigid rotation. And it is a big Julia set of this quadratic polynomial. So it is just all pre-images of this Ziegel disk. The critical point is here. The critical point of our quadratic polynomial is here. And if you start to blow up, you see that the Julia set looks very much self-similar near this critical point. It's already kind of indicated already on this picture. You have these little limbs that scale down to the critical point, and you see that there is some self-similarity features. But if you blow up, it goes. You can see this beyond any reasonable doubt. So once you have some self-similarities, and there should be near the critical point, then there should be some renormalization theory which is responsible for this self-similarity. And indeed, one can set up the normalization theory. And the key for this setting is that actually critical circle maps, so discussed before, can be turned by means of certain surgery, so discovered by Dodi and Gis in the 80s, to Ziegel maps. There is a deep relation between the critical circle maps and Ziegel maps. I don't have chance to have time to discuss this in detail, but there is some deep relation which allows one at least to start the normalization theory for Ziegel maps. And it was started in the 90s year. Well, so it is just some pictures illustrating the surgery. So let me not go here. Maybe let me just say one word. So this is the Julia set of some map, which is of some Blaschke product, some rational map of degree 3, which has this circle invariant, and it restricts to the critical circle map, so to circle homeomorphism with one critical point right here. Now, if you remove a lot of decorations from here, then you obtain such picture, and you see that this picture topologically looks pretty much the same as the picture of the Ziegel-Julia set. And indeed, one can justify that this picture, which comes from the Blaschke product, which keeps the circle invariant, is topologically equivalent to this Ziegel picture. Okay, so there is some deep relation which is promising in study of Ziegel maps. And indeed, this study was started by Kurt McMullen in the 90s, who showed, so using the circle theory, who showed that indeed, and by using analogies with the quadratic-like theory, that indeed the Ziegel renormalization has plenty of fixed points corresponding to various rotation numbers of stationary time. For instance, think about the golden mean. So for the golden mean, so there is a Ziegel map which looks exactly the same in all scales near the critical point. However, this theory came short of establishing hyperbolicity of this renormalization fixed point. So it tells it's a sort of justified self-similarity of the Julia sets of the dynamical pictures near the critical point, but it did not justify self-similarity of the parameter planes. So that is pieces of the parameter plane. So that is actually part of the main cardioid of the Mandelbrot set. So if you remember the Mandelbrot set, the most distinguished feature there is this huge main cardioid. It is little piece of this main cardioid. So the points here on the boundary, on this main cardioid, they have a neutral fixed point, and many of them have Ziegel disks. In particular, the Ziegel disk with golden mean rotation number sitting somewhere here, and there are certain limbs which converge to this golden mean rotation number, to this golden mean Ziegel point. Now, this picture is completely undistinguishable from that one, but it's not the same picture. It is actually this picture blown up in this region. You take some window that you like and you blow up the picture to this size, and you see that you obtain something completely undistinguishable. So there is this obvious parameter universality, which must have some explanation. And we know when we see some parameter universality, parameter self-similarity, it means that there is a normalization series. So we anticipate that the fixed point, which was constructed by Macmillan, is actually hyperbolic with respect to the renormalization transformation. But this problem resisted for also almost for basically 20 years, and it was resolved only very recently. So in the joint work, it's just the result of this year. So result joined with two young people, Dima Dudko and Nikita Selinger, which tells us exactly that the fixed point constructed by Macmillan is hyperbolic with respect to the normalization operator. There is a stable manifold. There is the stable manifold which has codimension 1, and in this case it just consists of Ziegel maps which have the same golden mean rotation number, and there is an unstable manifold of dimension 1. It is parameterized by the change in rotation number, and so this picture is responsible for self-similarity features of the Mandelbrot set. So it would require some work to justify, to derive from this picture self-similarity, and we don't have yet final results, but we already can establish rigorously some self-similarity features of the picture that I have shown you, of this picture. All right, so, and actually we needed to introduce a new type of renormalization, which we call Pacman renormalization. I actually had known about Pacman before, but I learned about them from my young colleagues. So here is a Pacman. It is some hybrid in between quadratic-like map and a Ziegel map. So you have some domain with some sector here, some sector removed, this domain, and it is mapped onto a bigger domain almost as a quadratic-like map, except there is a problem with one ray. So if you remove this ray and remove its preimage, removing the preimage in the domain, remove this ray in the range, then you obtain a quadratic, a Dublin covering map. So, but technically it is much, so that is the type of maps which we call Pacman. So, so you see this mouse of the Pacman, very dangerous. Very dangerous. Actually, all the technical difficulties come from this mouse. The boundary of this mouse goes to this special ray, which should be removed. So, and in this class of dynamical systems, we actually justified the previous result. So this hyperbolicity theorem that I quoted before, it is the hyperbolicity of certain kind of Pacman renormalization for which the fixed point is a Pacman map which has a Ziegel disk. So it is Ziegel-Pacman map. So, and it leads to above parameter self-similarities. Okay, so now, well, it is just, I'm reinforcing this property of scaling of the limbs, which comes from the normalization picture. But now let me go to some applications of this normalization series. It is to the problem of the area of the Julia sets. So if you have a quadratic polynomial, so I told you that the field Julia set is a set of non-escaping points, and the Julia set is the boundary of the set of non-escaping points, and it is nowhere dense set. So the most natural question to ask is whether the set has zero Lebesgue measure or positive Lebesgue measure. And this question is classical. It goes back to the classical work of Fatou, who gave first examples when the Julia set has zero area. And it was intensely investigated in the 80s and in the 90s, and there were many more classes produced of Julia sets, of quadratic polynomials for which the Julia set has zero area. But it was not still clear, so there is whether you can cover all the Julia set, and actually the sense started to emerge. Then maybe there are some examples of Julia sets of positive area. So several programs were set up in the 90s, so to attack this problem, and actually, well, one of the programs was set up by Dodi, who suggested to look for a Kramer point. A Kramer point, it is, so it also, the Kramer map, it has a fixed point, here it is put in 0, with differential, which is rotation. So with some rotation number theta, but it is not linearizable. So it is like Ziegel, but Ziegel is linearizable nearby, and Kramer points are not linearizable nearby. It is quite wild type of maps, which is not easy to understand. And Doherty suggested some program that these maps could be approximated by much better controlled Ziegel maps in such a careful way that in the end, in the limit, we obtain a quadratic polynomial, a Kramer quadratic polynomial with area of the Julia set positive area of the Julia set. And this program was brilliantly realized by two students of Doherty, by Xavier Bouff and Arnaud Chérital, about 10 years ago in the 20s. It is a very, very delicate piece of work. So, however, these examples, there are some shortcomings in this outcome. Namely, these examples of Kramer points, it is wild examples. It is not easy to understand topology of these Julia sets, dynamics on these Julia sets. It is very difficult, basically impossible to draw pictures of these Julia sets. And there are very few parameters for which this can be realized. So Julia set itself is big, it has positive area, but the set of parameters for which you can find these examples is a very tiny set of zero capacity, zero Hausdorff dimensions. So one would like to one wanted to create some bigger class of examples and maybe tamer class of examples which could be better understood. And this was done more recently, so it was about several years ago. It was done in the work with Artur Avila. So, and the examples that we constructed are exactly these Feigenbaum Julia sets. And Feigenbaum means infinitely normalizable Julia sets with stationary combinatorics. Take some stationary combinatorics. Not all of them have positive area Julia sets. One should work in order to construct, but we constructed such examples of infinitely normalizable Julia sets, Feigenbaum Julia sets, which have positive area. And these examples are tame. They admit a precise topological model, the dynamics, topological dynamics, and measure theoretic dynamics on these Julia sets is easy to understand, and they're quite visible. So there is a substantial set of parameters. So the Hausdorff dimension of this set is at least 1/2. So it is positive Hausdorff dimension for which such kind of examples can be constructed. Not with stationary combinatorics, but with so-called bounded combinatorics. And let me spend final several minutes just to give you some idea. So what is the basic idea how these examples can be constructed? You see, not how they can be constructed, but so what is the mechanism behind these examples? You see this renormalization scale. So we have this renormalization scale. So we have our map which look roughly the same in all the scales. And so let us mark these scales. So one normalization scale, next normalization scale, next normalization scale. And we want to understand how orbits pass from one scale to another. Take some point in deep scale and follow the orbit. The question, whether this orbit tends to go up to more shallow scales or it tends to go down to deeper and deeper scales. And if the probability on going up is high, dominates probability of going down, then the corresponding Julia set would have zero area. But if the probability of going down to deeper scales dominates over the probability of escaping to shallow scales, then the Julia set has positive area. So one can prepare such a result, so to set up some random walk scheme which would tell you exactly that. And then recently we showed that indeed one can construct an example of a Feigenbaum Julia set for which the probability of going down to deeper scales dominates over probability of escaping to narrow scales. And these examples, they use all the normalization theories which I described before. So there was a reason why I discussed this topic after the renormalization series. We need the Ziegel renormalization theory, including the parameter universality, and we need, of course, Feigenbaum renormalization theory, quadratic-like renormalization theory, which is built in the formulation of this example. I don't think that I have time for you to describe the construction, so let me skip this slide and let me just show you a picture illustrating this Julia set, this quadratic polynomial with positive area Julia set. So it is, we don't see the Julia set here. It is some quadratic polynomial, and we see some renormalization domain. This black hole is some renormalization domain for this quadratic polynomial, which is mapped as a quadratic-like map onto this bigger domain. So, and so we see this race, a kind of Hawking race, where of the orbits which escape from this fundamental annulus, so escape and never come back. And you see that the probability of escape is very small. These rays are very, very tiny, so they're very narrow. So there is a small probability of escaping from this horizon, beyond this horizon of this black hole. On the other hand, there are these, I don't know whether you see them or not, but there are these domains here which actually land in our black hole under some iterate of the map. And so they have a quite so big size. So you see that the probability of going down from this scale to a deeper scale is quite substantial. So this picture suggests that indeed probability of going down to deeper scales dominates over the probability of going up and escaping. So it is a good candidate for the Julia set of positive area. It is a type of the Julia sets that we have constructed, though of course for this particular parameter we don't know exactly whether, we don't know for sure that whether the corresponding Julia set has positive or zero area, but it is so the right type of example. So we are now looking right inside of the black hole in the center of our universe, so be careful, stay away from it, please. Thank you.